Yeah, I think the moment I said that, someone is already thinking, now that would justify getting a Bose, QC35, because I can now tell my parents, I need it for class. My professor said that I need it for class. You guys know what a QC is? The Quiet Comfort 35 from Bose. It's the flagship of all noise canceling Bluetooth headsets. Yep. All right, so let's go ahead and get started. I did get the A-star algorithm into the web page, so we'll see how far we can go today. Okay, so the first thing we'll do is we'll play with Dijkstra's algorithm, and we'll test out a few scenarios. We'll run the algorithm through actual graphs, and then we'll trace it. Okay, we'll figure out how the variables are getting updated and so on and so forth. Are there any questions before we start on the Dijkstra's algorithm? Okay, no questions. All right, so I'm just gonna start up all my various devices and whatnot. I should probably keep all of these things attached like it is and just push in a cart. I think that would make this job easier. Okay. Doesn't. I got into my tablet a little bit too slow, so it wants to do it again. Okay, we'll do it one more time. Nope. Okay. Detach and reattach. One more time. There we go. Okay. And then we'll first go back to the module. And let me get this out of the way. There we go. All right, so what we'll do today is to play with Dijkstra's algorithm. Because last time I kind of explained it already, if I remember correctly. Did I explain Dijkstra's algorithm a little bit? Okay. So what we want to do today is to use it to solve a few problems, finding the shortest paths within like one or two graphs, if we can have time to do it. So we'll switch to the tablet for the picture of the graph itself. So let me. Okay, this is actually what I captured last time, and we can start with this. So now we need to designate, which ones are the destinations. So let's mark E and C as destinations. So I'm going to mark it here. This is a destination, and this one is also a destination. So now we want to draw some edges, okay, between the other vertices to these guys. So we'll start one vertex from A to E, and then we want to define the distance. And typically when people draw directed graphs like this, they just put a number next to an arc or an edge, and that would be the distance of that particular edge. So we'll say this edge has a cost of, let's say, 10 units. Okay, and then we'll also have A going to C with I don't know, 15 units. Okay, and then we'll have A go to B with a cost of 1 unit. We'll have B going back to A with 2 units. And then we'll have E going to D with 3 units. That's actually irrelevant for the most part. And then we'll have D back to A with 6 units. Let's see. We'll just make it more fun. B to C has a unit of, say, 15 units. All right. So now we have a graph, and And Dijkstra's algorithm does not need you to designate a particular source. You don't have to tell it where you're starting from. You just have to designate which ones are your destinations. So in this case, as I said, vertex C and vertex E are our destinations. So we're going to look at this and try to figure out, okay, so what are we going to do with Dijkstra's algorithm? How are we initializing it, and how are we running it, and how does it find the shortest paths? Now with this one, the interesting thing is we're going to have to update information of a particular vertex a few times, okay? Because the first instinctive arc or the edge is not going to be the shortest one, okay? So we'll get to that part, okay? All right. So are there any questions about this particular picture itself, which is a graphical representation of the graph that we are trying to solve? Any questions about this one? Nope. Okay. All right. So if there are no questions about this, then we'll go back to the algorithm itself, okay, which is this part. And then we also need a way to track the progress of the algorithm. And I'm going to use a spreadsheet to do it. So this is going to look a little bit confusing because we have three things going on at the same time. We have the algorithm, we have the actual graph, which is a pictorial representation, and then we also have the trace, which we want to use because this is how we're going to track down how the algorithm works. So I'm going to put it into the share folder and put it here. I think it automatically makes it share to everyone who has access to this share folder. This is going to be, yep, okay, so it's creating it in here, create and share. And let me change the file name so that you guys can find it. So we'll rename it to 2018-0423. This is Dijkstra, Dijkstra's algorithm. Okay, so this is going to be how we trace the algorithm. So this will look a little bit confusing because, as I said, we have to kind of bounce between several screens. This is the trace. This is the actual algorithm. So what we want to do is, okay, the first line is done. Okay, let the graph be G equals to VE, blah, blah, blah. That's all done. We already have the distance function, which maps the edges to non-negative real values. So I didn't quite use a function to represent D, but I put numbers on the edges, so it kind of serves the same purpose. Number two is a subset of V, which are the vertices that are marked as destinations. We got that too. We got vertex C and vertex E designated as destinations. So we got that set already set up. Number three, okay, I'm just going to point out where we are here. This is number three. So number three is saying we want to initialize V in S. Okay, so for every single destination, the length of the shortest path to that vertex is defined to be 0. Is that okay? Okay, all right. So this is where we actually have some work to do. So I'm going to switch back to the spreadsheet. So there will be a whole bunch of switching around. So if you have any questions or want me to kind of stop or pause, just let me know so that I can stay on one screen a little bit longer before I switch back to the other screen. So over here we have a few things to track. We got Q, which is a set that we have to track later on. I'm not going to put the subset S here because we know the subset S only has vertex C and vertex E, and they are clearly marked on the pictorial representation. So I'm not going to do that. Then we have L of A, L of B, L of C, L of D, and L of E. So these are basically indicating the length of the known short path at this time. That's what the L function is indicating. So if I switch back to the algorithm, for something that is in the set of S, L of V is automatically initialized to 0 because from the perspective of a destination vertex, how far is it from a destination? 0. So it makes sense. For anything else, for anything that is not a destination vertex, the initial L of V is infinity because we're just saying we haven't explored the maze yet, or we haven't explored the graph yet. So we're going to make the assumption, the worst case assumption is it's not connected to a destination. So until we actually find out that it is connected, we make the assumption that it is not. And as a result, the length is infinity. So in this case, sorry about that. So in this case, we're going to initialize L of A to be infinity. L of B is infinity. L of C is a 0. L of D is infinity. L of E is also going to be a 0. In other words, only the two destination vertices get 0 for the initial value, and then for everybody else, they get infinity. Is that okay so far? Yes? Okay, excellent. All right, so getting back to the graph here. So at this point, what we have done is to say vertex A, because we have not explored anything yet, and vertex A is not a destination, we just say that you may just be hanging in outer space and there's no way for you to connect to any destination, so your L value is infinity. Same thing applies to B and D. And then for C and E, because they are destinations already, their L values are initialized to 0. I just want to give you the visual representation before we switch back to the more abstract algorithm representation. Okay, so switching back to, and then we go to the algorithm again. So we're basically done with these two initialization, the L values. So now it's time to initialize the set Q. So remember, Q is what I call the boundary or the frontier set, which is basically saying, okay, these guys just got some value. We just recently know how to connect these vertices to a destination, not directly through a path, but I know they're connected. Let's evaluate these things. So that's what the set Q is really doing. So switching back to here, so our frontier starts with vertex E and vertex C. Now going back to the trace, Q is initialized to be a set that has C and E in it. Those two are our destinations. So are we still doing okay? Is that font size okay, or do you guys want it to be a little bit bigger? A little bit bigger? Okay, we can do that. Is that okay? Or a little bit more? That's okay? All right. Huh? It's better? Okay. And I can always maximize the screen as well, because I will need more space later on. So I'm going to pull this thing down here. So this way the heading of each column stays visible, because the bottom part may need to scroll around a little bit. So switching back to the graph. Okay, that's not what I want to do. Oh, that makes switching to the other tabs a little bit harder. Okay, turn this into its own window. New tab. Where is it? Pin tab. How do I turn it into its own window? I know I can drag it out, but I'm looking for a keyboard shortcut to do it. I thought there's a way to do it, through a keyboard shortcut. I could be wrong, but that's okay. We can just pull it out and put it back in like that. And then we can maximize this. We can maximize this. And then we have the tablet screen, and we can maximize that too, but it's okay the way it is. All right. Okay, so now getting back to the algorithm. We are now done with the initialization of Q, and we want to initialize E prime. So E prime is basically the set of all the edges in what I call the solution graph. In other words, at the end of the algorithm, if we combine V and E prime, we'll get a new graph. That new graph only consists of the shortest paths from every vertex to a destination. So that's the job of the E prime. E prime is guaranteed to be a subset of E. Okay, that makes sense, right? So we'll go ahead and initialize E prime and put it into our spreadsheet here. So I'll put it right before this column. So we'll insert one column to the left, and we call this E prime. And initially it is an empty set, so there's nothing in it to begin with. And now we are ready to get into the algorithm. So when we get into the algorithm, the first thing is, are we done? Because if there's nothing in the frontier set, that means every vertex is already done in the sense of they're fully analyzed and I'm not leaving anything that can potentially connect to a destination cell and it's not yet connected. Yep.
Yeah, algorithm perspective, it seems like you're looking from the destination to
Yes.
anywhere else.
Yes, we are starting with destinations and we're going quote unquote backwards to figure out, how long does one particular vertex to get there.
Okay.
Yep. So the other way to look at this is, okay, I think most people will remember the analogy and not really the point of the analogy again. So think about it this way. So you have a little maze setup, okay, fully enclosed, but it's a maze. So in the maze, you have several spots where you put like cockroach poison, bombs, okay? So they generate gas to kill cockroaches. Is that okay? And then you have one cockroach per cell per location. Is that okay? So we want to figure out, which cockroach is the first to die, which one is the second to die, which one is the third to die, and so on. Is that okay? The locations where the insecticide bomb is located are the destinations. And then we are basically propagating the poisonous gas backwards to the cockroaches in order to figure out when a particular cockroach is going to die. That actually is how Dijkstra's algorithm works. If you want to visualize it, that's kind of how it works.
What's it called?
Huh?
What's it called?
Dijkstra's algorithm.
Can you spell it?
It is in the notes. I'm sorry, yeah, okay. So Q is obviously not empty at this point. We have two vertices in it. So now we want to select one of the vertices out of Q. And we want to select one that has the least value, the least L value. So if we switch back to the spreadsheet, we look at, okay, what's in Q? C and E. L of C is 0, L of E is also 0. So it doesn't really matter which one we choose because they have the same L value. Which one do you guys want to pick? Pick one. Hmm? How many want C as the start first one? And how many wants to vote for E? Okay, so I'm turning this into a mini election, right? So C it is. All right, so I'm going to insert a new column here because we want to remember which one we have chosen, because otherwise it becomes kind of difficult to remember, oh, which one did we pick again? So we just want to remember that in the first iteration of the outer loop, we picked C as a vertex to be our variable V. So V is a variable, C is not, okay? C is really just the name of the vertex in that case. Get back to the algorithm. The next thing we do is we want to remove that particular vertex, the one that we have just picked, from Q because, hey, we are now exploring this one, so it's no longer in the frontier. So we go back here, and then we update Q, so the Q does not have C anymore. Now it has one single vertex in it, which is E. Switching back to the algorithm, next thing we do is we say, oh, let's look at all the incoming neighbors of the vertex that we have chosen. The vertex that we have chosen is vertex C, okay? The name of the vertex is C. So now we want to say, okay, who is going into that vertex? For each incoming neighbor, we want to go through this code, okay? So getting back to the visual representation, this is vertex C. How many incoming neighbors do we have? We got two, okay. So we got two, one is here and the other one is here. Okay, so this time it doesn't really matter, okay? There's no sorting when we are considering all the incoming neighbors. So you can explore B first if you want. You can also explore A first if you want. It doesn't really matter which one. So in the algorithm, we just have to randomly pick one. We just have to make sure that all of them are considered in this for loop. So going back to the trace, which one do you want to choose? This is our incoming neighbor, and in the algorithm we call that W. Okay, so W is the incoming neighbor of the vertex that we have chosen. And which one do you want to choose? A or B? B, okay, so we pick B first. All right, so now that we have chosen the edge WV, which connects to the vertex that we have chosen. The first thing we say, okay, we'll call it edge E. Okay, so that's not really a big deal. And then the next question is a comparison. Now, whenever we have a comparison or a condition, it is really significant because it is a point of decision making. So that usually has a lot of significance in any algorithm. So this one is asking, is the current L of V value plus D of E, is that less than L of W? Okay, but what is the meaning of this comparison? So that's the important part, is what is the meaning of this comparison? L of V is the length of the shortest path to vertex V at this point. Okay? L of W is similar. Okay? It's the length of the shortest path to W at this point. We know E connects W to V with a distance of D. Is that okay? So when you look at the left-hand side of the comparison, it's basically saying, oh, we might have just found an alternative path from W all the way to one of the destinations. And L of V plus D of E is the exact length of that particular path. Is that okay? And now we're comparing against what we currently know as the length of the shortest path from W to one of the destinations. If it is less than, guess what? We have just found a shorter path. It may not be the shortest yet, but it is shorter than the one that we already know at this time. Is that okay? It is still an improvement, so we're going to make some changes. So at this point, we know that L of C plus the distance of the BC edge is 15, and 15 is less than L of B because L of B is infinity at this point. So the condition is true. So we go back to this trace here and say, okay, the condition is true because L of B is infinity, L of C is 0, and then the distance of going from B to C is 15. So that's why we're going to go into the conditional statement. So in the conditional statement, the first thing we do is update the length of the shortest path from W to one of the destinations. Kind of makes sense, right? Because we just found a shorter path. Let's remember the length of that shorter path. So what is the numerical value this time? If I were to update this number, what is it going to be? 15, exactly. Okay, so 15 is good. So we just update it. We just update this guy. And then we move on here. This is really just a long way of saying erase everything that is going out from B in E prime. Do we have anything in E prime that represents edges coming out of vertex B? Let's check. E is empty. So there's nothing, right? There's nothing to remove. Okay, so we're done with that process. And then the next thing we do is we update E prime and say, well, this edge here, which is from B to C, may be one of the shortest paths edges. Let's put it into E prime. So E prime is now updated to include that edge, which is from B to C, like so. So I will change the width of these columns as we need to. So some of these will get bigger and some of these will get, well, they won't get much smaller, but they might get bigger. Whew, thank you. Okay, so the next thing is also important. Okay, we're done with E prime getting updated and we're adding one more element to E prime. But Q is important too, because we just updated the L value of vertex B. In other words, oh, anything that goes into vertex B can now potentially get a new shortest path too. So that's why we're adding vertex B into the frontier set, because it itself just got updated. And as a result, anything that goes in to vertex B may need an update as well. That is why we are adding vertex B into the frontier set. So now we go into the trace and we just say, oh, okay, Q is now updated. We have B and E in it because we just added vertex B into it. So getting back to the algorithm, that completes the inner loop, which is the for each loop, one iteration of that. But then we go like, oh, wait, there's another vertex going into vertex C. We just considered B. Where's the other one? Let's check. So we are looking at vertex C here. Vertex B is one thing that goes into it. The other one is vertex A. Okay, so we are not quite done with the for each loop yet. So now we have to go back to the spreadsheet and say, oh, okay, I guess we also have A that can serve in the role of variable W, because WV is an edge that is going into the vertex V. This is the other one. So we're going to ask the same question, and it's going to come up with the same answer. In other words, we are asking the question, if we look at L of C, which is 0, we add the distance of the edge going from A to C, which has a distance of 15. 0 plus 15 is 15. Is that less than the current L value of vertex A, which is infinity? Well, is 15 less than infinity? Yep. Okay. Yep. So that means we have to go into the loop again. Or, excuse me, go into the conditional statement. And then we have to update L of A in this case. So L of A is going to be updated to 15. And then we have to remember to remove all the edges going from A to anything else. There's none here, so that's good. We're all safe here. But we do have to add that one edge at this point. So now it is BC and AC here. So those two are now in our quote-unquote solution set of edges, because at this point, based on what we have explored, these two are representing shortest paths of those respective vertices. Okay, are they actually the shortest paths? Well, I guess we'll find out. But we also have to remember to add vertex A into the set Q, because vertex A just got its L value updated. So we have to say that, okay, we're going to put you back into the set Q so that we will evaluate all the vertices going into A, because they can potentially be updated as well as a result of this. So are we doing okay so far with the algorithm, with the trace? Okay. So going back to the algorithm, so we are done with another iteration of the for each loop. This time we are done with the for each, because we only got 2 incoming edges into vertex C, and we got both of them handled. We're done with the inner loop. Out of the for each loop, there's nothing else to do in the while loop. So we go straight back into the beginning of the while loop, and then we ask the question, are we done? No, Q is not empty. Q, in fact, has 3 elements now. We used to have 2. Now it has 3 elements. So since we are not done, we have to go through the selection process. In other words, we choose one vertex out of Q that has the least L value, because that looks the most promising. Okay, so at this point, which one looks the most promising to you? Yep, because when you look at this, you can look at C and go like, but C still has a value of 0, but vertex C is not even in Q. We only want to consider the elements in Q and ask which one of the elements in Q has the least L value, and E is the one that has the least value. So in the second iteration of the while loop, we say, okay, we'll pick out E as our vertex vertex V, and then we have to remove it from the set Q. So set Q is now just AB without the E, and then now we have to evaluate all the incoming edges to vertex E. It is easier to see it in the graph like this. So we are looking at E here. E is easy because there's only one incoming edge from A. Okay, so we go back to here and we say the only incoming neighbor of E is vertex A. Then we ask that question again. Okay, we look at L of E, which is 0. We add the cost or distance of the edge from A to E, which is only 10. Okay, so that's a total of 10. In other words, we know now from A to a destination, it only costs like 10 units of distance. And then we now compare that to L of A. L of A is no longer infinity. It's 15 right now, but guess what? 10 is still less than 15. In other words, we now found a shorter path from vertex A to one of the destination vertices. Is that okay? So now we go through all the updates again, because we have to go into the then part of the conditional statement. So L of A is now updated to a 10. And this time we do have to remove an edge from A to something else, Because guess what? That edge is no longer on the shortest path from A to a destination. We just found a shorter way. So we have to remove AC as an edge from E from E prime, and then we have to add the new edge, which is AE, back into E prime. Is that okay? Are there any questions about this update to E prime as a set of edges? It's all good? Okay. Then we got one more thing to do, because remember, we just updated the L value of A, which means anything that goes into A can potentially be updated. So we are adding A back. We are adding A to the vertex to the set Q, which actually doesn't do a single thing to Q, because Q already has A as an element. So by unioning the set Q with the set that only has A didn't do a single thing, because A is already in that set. Is that okay? Now, since A is the only incoming neighbor of E, we are now done with the for each loop. Okay, let me switch back to the algorithm. So we are now done with the for each loop and getting back to the outer loop, which is a while loop. Q is not empty. It still has two elements in it. So we look into the two elements, and then we go, okay, well, of the two elements left in Q, which one has the least L value? So A has a L value of 10, B has an L value of 15, so we're going to pick A this time. So we're going to say, okay, vertex V or variable V is now A. So now we have to evaluate all the incoming neighbors of A. So now we switch back to the graph representation. We go like, wow, we got two edges coming into A, because B is going into A and D is going into A as well. Doesn't really matter which one we choose first, because we have to hit them all. So we'll just say, okay, let's go from left to right. Okay, we'll deal with B first. And then we also want to remember the edge from B to A has a distance of 2. So we go back here, and then we evaluate B. We evaluate L of A first. L of A has a has a length of 10. You add the 2, it becomes 12. Is 12 less than the length of B going to a destination? Yep, because the known length, the length of the known shortest path is only 15, and we now have a path of 12. So I need to update this one to be B. Okay, there we go. So we have to update L of B to 12 now. Is that making any sense? And as a result, we have to remove BC from the set E prime, because we just found a shorter way to go from B to a destination. That old edge in E prime doesn't work anymore. So BC is now gone, but then we have to add BA into E prime. So BA is now in E prime. AE is still there. Is that okay? Is the update of E prime okay? Yes, go ahead.
Would it be wrong to put AB instead of BA? I mean,
That would be incorrect, because it's a tuple, so that means ordering is important. Because BA represents an edge going from B to A, and edge AB represents an edge going from A to B, so they are distinct. Yep. But that's a good question to ask, because it's always good to double check. Okay, well, since we just updated the L value of B, let's add it to the set QB. Oh, I forgot one thing, sorry. Okay, this is, my omission is here. I forgot to take A out of Q, so that's why, it will just be B at this point, because we just added B back into Q, which already has B, so it doesn't really change the value of Q at this point. Cool. Do you guys remember which vertex also goes to vertex A? Good memory. Okay. So D is also going to A. D is going to A with a distance of 6. Okay. All right. So we go back here, and then we say, okay, now we pick D as an incoming neighbor to A. And once again, we calculate L of A, which is 10, plus the distance of the edge of D going to A, which is 6. 10 plus 6 is 16. So now we say, okay, is 16 less than the current length, the length of the current shortest path to D? Oh yeah, infinity is definitely more than 16. So once again, we got a few updates here. 16 over here.
The mouse cursor isn't
Huh?
the way the mouse cursor.
Oh, okay. There we go. And we also have to remember to remove all the edges from D to something else. Since there's none here, we don't have to remove anything. So we keep everything as is, and then we are just adding this new edge, which is going from D to A into the set of all the solution edges. And because we just updated the vertex, the L value of vertex D, so we have to add D into the set of Q. And that ends the inner loop. Then we go back to the outer loop again. So when we go back to the outer loop, okay, which is all the way back to here, Q is not empty. Q has got two elements. So of the two elements, now we want to find the one that has the least L value. Okay. And then we look at this trace here and go like, okay, which one has the least value? So we only have to compare L of B versus L of D. L of B is 12, L of D is 16. Of these two, L of B is the one that we should choose. So that means, you know, this time we are choosing B as vertex V as a variable. Is that making any sense? And as a result, we have to take it away from the set Q. Now we have to evaluate all the incoming edges to vertex B. So we look at the picture here, and we go like, okay, who's going into vertex B? Ah, interesting. Vertex A goes to vertex B. Okay, so vertex A is something that we have revisited quite a few times. But that's okay. This is the last time we will see it. Because we put it here, and then we ask the question, have we just found a shorter path from A to a destination? In other words, yes, go ahead.
I was going to say, so the objective is that you keep going into the loop until you find the best destination?
We start with the destination, okay? So we keep going through the loop until there are no vertices in what I call the frontier set.
All right, so you keep going until there's no vertex until the very end?
Well, the algorithm is all spelled out. I'm just kind of running through it at this point. Okay, what was I doing? Right, okay, so L of B has a value of 12. What is the cost of the edge from A to B? I think it was 15, right? Yeah, I can just kind of go back and check. Okay, so the edge going from A, vertex A, oh, it's a 1. Okay, there we go. So from A to B is only a cost of 1. Okay, so we have 12 plus 1, which is 15. Huh? 13. Oh, okay. Misspoke.
No, you was looking at that, but you had it in your head.
That's why I think I can make a perfect politician. I can look at one thing, say another thing, and totally forgot that I said it. And I would pass the lie detector test with flying colors at the same time. Because I actually did not remember and misspoke without even knowing that I misspoke. Okay, so anyhow, 13. Okay, 13 it is. So we have just found a path from A to a destination with a length of 13. Is it less than what we know at this point? Nope. 13 is not less than 10. So this time we are not going to go into the conditional statement. So there's actually no update this time. Cool. So that means going back to the pseudocode here, we are now done with this conditional statement because this condition is false to begin with. And because that was the only edge going into vertex B, we are now done with the for each loop. So that means now it's time to go back to the outer loop and we ask, is Q empty? Well, not quite, but pretty close. So with only one vertex left, we have no choice but to choose it. We don't even have to ask what is its L value. We have to choose it. So we choose D at this point, and then the Q becomes an empty set. And then we say, okay, who is going into vertex D? Okay, so let's look at the graph here. Vertex D has E going into it. Now that is funky because E is a destination already. Well, but nobody says that a destination vertex cannot go to some other vertices. Okay, it's totally valid. It's just that is our algorithm going to catch this and go like, ha, no updates this time. Okay, so let's find out.
I hope so.
We certainly hope so, because otherwise Mr. Dr. Dijkstra will not be very happy in his grave. Yep. Okay, so we are now evaluating this particular statement here. L of, okay, this is E, which is a destination, that's a 0. And we already know all the edges have distances of non-negative. So that means the condition has to be false. There's no way for this condition to be true. Go ahead.
So yeah, I was. It says E over there. I thought it was updating E prime.
Oh, okay. So getting back to the trace here, we are basically looking at, okay, so we put E here. So what we are trying to do is to compute L of D plus the cost of the edge from E to D. Okay, so the length of vertex D going to a destination is already 16 to begin with. And then 16 plus the distance of the edge from E to D. Okay, so let's check that. I cannot remember what it was. From E to D is 3. E plus 16, 3 plus 16 is 19. And we are comparing against L of E, which is a 0. 19 is less than 0 is false. Okay, so that means when we go back to the trace, there's nothing to do, there's nothing to update because the then condition does not, the then statement does not execute. So now we are done because now we go back to the main loop, the while loop. Okay, let me go back to the while loop here. Q is in fact empty at this point, and we're done. Is that okay? So now the question is, what exactly is in E prime? Okay, so let's check the trace because the trace will tell us what is in E prime, and I'm going to update the actual graph accordingly so that we can visually see what edges remain in E prime and which ones are gone. So we'll just spell these out one by one. We have BA, okay, so we go back to the graph here and use a different color. Okay, green is good. Okay, which one again? BA. Okay. Does that make sense? The BA should be the shortest path, okay, or on the shortest path from B to A. And let's see, what else? AE, okay, so A to E. So A to E is here. And then we got one more, which is D to A. Okay, so D to A is here. So the ones that are highlighted, green are in E prime. So the question is, does that make sense as a solution graph? Yep.
If what about the distance from A to B?
From A to B?
Yeah, since it's 1.
So A to B is 1, and what about it? B is not a destination,
Oh, okay.
and A is not a destination either. Remember, our destinations are C and E only. Okay, so what we want to do is to do a little sanity check, okay? So we go through every single vertex and just eyeball and visually say, okay, which one is the shortest path? Let's start with A, so we will sequentially go through the vertices. So let's start with A. In order to go to one of the two destinations, which way is the fastest? A to E has a cost of 10. A to C directly has a cost of 15. If it goes through vertex B first, then it has a cost of 16. Yeah, so that seems to make sense, okay? A to E directly using that edge of, a distance of 10 seems to make sense. Okay, yep.
So we're choosing the shortest either between C or E, right?
That is correct.
Okay, that makes sense.
Yeah, so you can kind of imagine A, B, and D are little boys in a theme park, and then C and E are the bathrooms. Any bathroom would do, right?
Whoa, it gotta be clean though. I ain't sitting down on no that's no rats look like they
Assuming the bathrooms are in similar or equivalent hygiene condition, so they can be equally dirty. Yep.
So you do discount one destination.
Huh?
If you have two destinations, you're saying which one is the shortest destination from all
Yep.
of them.
And the Dijkstra's algorithm can handle. It can figure out. Oh, you're actually closer to this destination, so it will the shortest path will guide the vertex to that destination. Okay. So yeah, go ahead.
This doesn't necessarily handle a specific destination, correct?
It handles multiple destinations. So if you designate multiple vertices as your destinations, then it will just find the shortest path to a one of the destinations. Because okay, think of it from the perspective of, let's say, dining. Okay, so I want to get to the closest. I don't know. I was about to say Denny's, but I don't like Denny's.
Oh, what? IHOP.
Oh, better. Oh yeah, better. Yeah. So let's say IHOP, right?
Okay.
So we'll go. I just want to go to an IHOP. Okay. So does it matter which IHOP I want to go to? From the perspective of this problem, it does not. Okay. Unless you have something to do after going to IHOP, but that's a different problem now. It becomes a routing problem and not just finding the shortest path.
Okay. Oh,
Yeah.
so pretty much when I said the clean bathroom part, that'll be a routing problem, not a destination problem.
Why? Why would the cleanliness become a routing issue?
It's because you want to go to the nearest but the most cleanest bathroom, and maybe that one's a little bit further than the closest one. Is pretty much, so that be a routing? Would that be also routing or no?
I think in that case you have to factor that into your distance, because the longer the distance, the more time it takes, and then the more urgent it becomes to go to a bathroom. So you have to factor that into your distance function. Yes.
It's one of those distances, so we can't let's change that example to restaurants. I want to do a Mexican restaurant.
Hmm.
That one's 4-star, that one's 5-star.
It doesn't take into consideration. So it does not prioritize amongst the destinations. Because if you want to prioritize among the destinations, then you have a problem, because now you have to weigh the length of the path versus the prioritization of your destination. And there's no, the algorithm itself does not factor that in. So there's no quick and easy solution if you want to kind of factor in prioritization of the destinations and also find, quote unquote, the shortest path, because you need a weighing function to basically say, yeah, yeah, do I drive 15 more minutes, or do I go to a restaurant that is not as cool as the one that I really want to go? I mean, that becomes a weighing option. You first. Yep. Yeah.
So for instance, like when looking at it, from D to get to E, you go through A. Is that with the consideration that A is the only route to get to E, or
No.
does it not consider?
Well, okay. So in this graph, yes, because there's no way for D to go through anything else to go to E, but it can go through A to go to some other destinations. But the thing is, if A is already on the shortest path and D connects to A, then the only time you really have a choice is D also connects to another vertex that also goes to the shortest path. Then it becomes whether the edge of D going to A and the edge of D going to the other vertex, which is also on the shortest path, then it becomes a toss-up between those two factors.
So it's then a consideration of all the possible routes that are available.
Dijkstra's algorithm consider all possible paths already, and it will find the shortest ones for each vertex, which is what we have here.
And question: do they all have to potentially do all the points A, B, and D? Do they all have to go to the same restroom, or can one of them, like let's say for instance, B go to C in case it's shorter instead of? I mean, obviously with this example it's not, but if it was shorter, can B go to C?
Yeah.
And then A go to E?
By changing these distance, values, it can dramatically change, how the graph is constructed.
Okay.
Yeah.
So they don't
This
have
is,
to go
yeah,
to the same.
exactly. But you are guaranteed that the solution graph, which is the green arrows here, trademarked, The moment I said they go like, oh, pattern matching, it matches a trademark. Um, so the key is, when you look at the solution graph, V E prime as a two tuple, that's a forest. It's guaranteed to be a forest. In other words, it is guaranteed to be a bunch of trees. There cannot be loops, for one thing, and there cannot even be two different paths from one vertex to another vertex. Guaranteed. There's only one path, up to one path, from any vertex to any other vertex. Even if they're equidistant. If they are in fact equidistant, then it depends on, remember when we pick something from Q, we said, okay, we have to pick the vertex that has the least L value, but we can only choose one at a time, right? That determines, if you have two paths of equal length, which one are we going to use? That basically, determines which one we're going to use. But it doesn't really matter, because if they have the same length, then they have the same length. Either way it's going to be the same. Question?
Yeah, I think it's two different questions. So, in just looking at E prime, the tuples that don't include a destination, there's like with the
Yeah.
tuple BA.
Yeah.
How do we know what to do next?
Well.
Or like from D to A. Right?
Well, okay. So when you distill this and only look at the E prime, so you take out all the other edges, okay, and you just look at the edges in E prime. That's a graph where, starting with any particular vertex, there's only one outgoing edge, up to only one outgoing edge, and that outgoing edge will always guide you to the shortest path to a destination.
Okay.
So it's a universal solution to all vertices.
So, but looking just at E prime itself without a graphical representation.
It's still helpful.
Oh, I see. Because they all end up in follow the tuples.
Right, correct.
Okay.
So, so no matter what vertex you're on or whatever vertex you are interested in, you just say, okay, in this particular set of edges, which edge has the vertex that I'm interested in as the tail?
Yeah. Okay.
We call it the tail because it looks at the head and the tail in the sense of an arrow. So the tail of an arrow is where you start. The head of an arrow is where you end up with.
Okay.
And the first item of a two tuple is called the tail of an edge. Yep. Go ahead. Sorry.
Okay. And then, just so I understand, if there was another vertex between D and A,
Between D and A.
D to X, let's say it's a distance of 3, and then from X to A, it's also a distance of 3. So that total distance doesn't change. E prime would change in such a way where it's X to A instead of D to A, correct?
That it would include two edges now, because this vertex that is in between will go to A, and then vertex D will go to whatever vertex is in between A and D.
Okay, so D to A would be removed, but then D
Correct.
to X would be included, and X to A would be included.
That is correct. But it would not impact anything else, because the total length of that segment of the path is still the same. It is still 6.
Okay.
So it would not impact any of the other vertices. So is that okay? This is Dijkstra's algorithm. Yep.
Okay. The thing, all right. So the question will go like this: what's happened if, like, we say, like, if we assume that there's like obstacles and like there's obstacles, like for example, define a route but you cannot go through X or Y areas.
Then you wouldn't have an edge to represent
Okay.
that route that is blocked.
Oh, okay.
There's no edge for C to D, so that can't be represented, right?
Yeah, like in this case, okay, there's no edge from C to D directly, so that means there's if these are locations on the map, okay, so that means there's no road directly going from C to D.
Oh, so you only just put the edge where there's legit connections.
Well, you can always do this, but it doesn't really do anything useful. Okay, I shouldn't use that color, so I'm going to choose a different color here. So you can always do something like this and call this, having a distance of infinity. I mean, the Dijkstra's algorithm will take this in and use it correctly. It's not going to come up with a wrong solution. But the question is, why do you want to put an edge like this into the graph? Because it is as if it is not there.
Plug into space.
It doesn't do a single thing. Yep.
Because what happened is like a lot of GPS companies are getting sued because they keep putting the map marking inside of neighborhoods and they're getting flooded. That's why I asked that question because I remember in the last class you was talking about like the whole PISA thing.
But that's easily solvable because basically when the GPS is directing traffic too much through a particular neighborhood, the distance corresponding to those edges will automatically increase. You just have to you update these values dynamically, and then you rerun Dijkstra's algorithm, and the new route is going to reflect a shorter path. Now, the fun part of that approach is if it's all kind of happening in random times and people are not doing it all at the same time, it will work. Okay, in fact, it will find a equilibrium, so that everybody gets to the destination at about the same time, even though they're all going in different routes. Now, what is interesting is if everybody turns on the GPS and search for that destination at exactly the same moment, then they will all be flooding through the same route, right? And then when they're stuck in traffic and they all go, okay, I want to update, and they all hit that update button at exactly the same time, then it will oscillate to the alternate path. So it's going to alternate, it's going to oscillate instead of settling on an equilibrium state. It will actually go into it will go into an unstable bimodal state, and it will just kind of oscillate. Yep.
So you said that so for that to fix a problem you increase the edge or what did you
You increase the distance of the edge.
distance of that. Oh, and by the way, I found a simple solution for that. What happened is that you just use a scheduling or a priority type program. So like you total up all the requests and then have the computer to cut it by half, rounded to the nearest mod, and then have that to go that way, and then do the next priority of that to go that way. Just use the scheduling algorithm.
Okay, well that doesn't sound like a path planning type of algorithm anymore. I cannot tell which one is first. Okay. Okay, go ahead.
I was wondering, did you talk about the big loan notation for the?
No, not yet. Not yet. Yep.
As far as like the preparation for like the final and stuff like that, how would you expect us?
That's a good question.
On this graph,
Okay.
how do you want us to?
So that's a very good question. So let me repeat the question so it's recorded. So the question is, with respect to the Dijkstra's algorithm, how do we prepare for the final exam? So that's a very good question. Okay, first thing first, make sure that you have the algorithm with you. Okay. Okay, so print it out. It's open book, open notes, just like the first and the second exam. So anything that you can find on the internet, not just my notes, is fair game. Okay, first thing. Second one is some question may come in the form of I give you a graph. Just like this one before the green labels, I give you a graph, and the question will be in the form of trace it and show me that you understand how the algorithm works. In other words, I'm not just asking for the final E prime. I want to know how you get to that conclusion. So you can use exactly this format because I use it in class. So you can use exactly the same format to indicate how the variables got changed when you execute the algorithm. Yep.
I'm asking because I feel like you might ask, like, you might want to weigh the values, like, okay, now I want to go to the 5-star restaurant, so now I value this path at like, decrease the distance by, or multiply by 0.8, and that's how much I would weigh the distance. And do we want to update the graph essentially? Would you be asking those kind of questions?
If you change the distance of one particular edge, you typically just rerun the entire algorithm because unless there's a very clear partitioning and that edge would not impact anything downstream, but it will only impact stuff that is upstream. So unless that is the case, you typically just have to rerun the entire algorithm. Yep.
So if we like had some tests, since we learned this in 440 last semester, I I liked the way he did it a lot. Like I understood it a lot better. So if I explained his way a lot more, like if I explained the way I did it and not necessarily doing your exact way, that you'd be okay with that.
You might want to show me ahead of time.
Because we did it in stacks.
Okay.
And so like the shortest route would always get in the top of the stack. And then we go through
That would not be a stack anymore. It would be a.
I can't remember.
they call it a heap, right? A heap.
Oh yeah.
Yeah, a heap makes sure that the first item is the smallest, but then the rest may not be. Yeah. So you can use that also, but using the concept of a heap means I have to introduce the concept of a heap as well.
I mean,
Yeah.
for me, that I know.
Yeah. So if you want to use that terminology, that's fine with me. I understand what a heap is. Yep. Yep.
I noticed that when you updated Q, you updated adding to the front of the.
It doesn't matter because it is a set. So just because notation-wise I put it to the front doesn't mean that the ordering has no importance. And besides, we only choose elements from the set Q based on the L value. So even that positioning inside the set Q doesn't really have any meaning because the way we choose is the one that has the least L value. Questions? I thought I saw another hand. No. Okay. So what do you guys think about the Dijkstra's algorithm? Okay. It is not very resource intensive. Okay, so here comes the order of magnitude. Okay, so I know we haven't formally introduced what is the big O notation, okay, which is an estimation of how long it takes to execute an algorithm based on the size of the problem. In other words, if I double the size of the problem, okay, is it going to double the time it takes to complete the algorithm? Is it going for 2 to the squared? Is it going to be 2 to the cubed? Is it going to be the factorial of the size of the problem? And so on and so forth. Okay, in other words, I'm looking for the relationship between the size of the problem versus the amount of time that it takes to complete the computation. So what do you think in this case? So let's switch back to the algorithm itself. What do you think is the ultimate limitation? It cannot exceed this. Okay, what is n? We got a few things here. We have the number of vertices and we have the number of edges. So you got to, which one are you talking about? We have 2 cardinalities that can potentially have an impact on the runtime of the algorithm. So the question is it proportional to the number of vertices or is it proportional to the number of edges? Which one matters? Okay, I'm not even talking about is it squared or cubed or something. Which one matters? Edges, exactly. Because I can give you a graph with 20,000 vertices but no edges whatsoever, right? And then I ask you how long would it take to execute the Dijkstra's algorithm? Not 0. It goes through one single iteration, assuming there's one single destination. It will still go through one iteration because the number of destination vertices determines how many times you have to go through the outer loop at the minimum. Okay? No, one time. Because you only got, assuming there's only one destination vertex. Now, obviously, I can also ask a trick question. What if all 20,000 vertices are destinations? Then, technically speaking, you have to go through 20,000 times. So in that case, it's kind of proportional to the vertices, but the chances of that happening is really low. Okay. Say that one more time.
So how much would each destination increase the big O?
It will be, okay, so that's the minimum. Okay, so if you want to go for, so there are 3 notations. There's big O, there's big theta, and then there's big omega. Big omega, I think, is the lower bound. Big theta is the average, and then big omega is the upper bound. So the lower bound is going to be the number of destinations. You cannot go below that. There's no way you can go below that. Is that making any sense? Huh? Yeah, best case scenario. You cannot go below that. But what about the worst case scenario, which is what most of us are concerned about, is in the worst case, what does it look like? In the worst case, it'll be edges because how many edges can you have given, X number of vertices? If I proportional to X squared, okay? So let's look at this. This is something that we have seen already, but it doesn't It doesn't hurt to see it again. Okay, so let's say we only got 2 vertices. Okay, so with 2 vertices, assuming it is non-directed, because directed means you just double it. Is that okay? So assuming this is non-directed, we got 1 edge. If you have 1 vertex, it has got 0 edges. Is that okay? What if you have 3 vertices? You got 3 vertices, right? So now, here's the magical part. If I just add 1 more vertex, how is that going to change the number of edges in order for everything to be connected to everything else using a single edge? Add 3. Yep, exactly. 3 more, because I can now have an edge from A to D, C to D, and then B to D. Okay? So it becomes, and what if I add 1 more? Then we have 4 edges, right? So it's basically a problem that we have seen before. If n represents the number of edges, then the number of possible edges in, excuse me, if n is the number of vertices, then the total number of possible edges in a completely connected graph would be be a summation. It's a sigma notation. Okay, let me just write it down because it's harder for me to say it. Okay. So we'll say n equals to the cardinality of v, just so that I don't have to say the cardinality of v all the time. Okay. Then the number of edges, or the cardinality of edges, is going to be less than or equal to the summation of I going from 0 to n minus 1 I. Does that make sense? So every time n increases by 1, you just say, oh, we have n minus 1 more edges compared to before. But we have seen something like this before, not exactly, but something like this, right? We had, last time we just didn't have this. And this time we have this. That doesn't really change the order of magnitude. So what was the order of magnitude from before? It's n times n plus 1, the whole thing divided by 2, right? So this time it is n times n minus 1, the whole thing divided by 2. So of that term, which term grows the fastest? Okay, let me spell it out. Okay, so we got n times n minus 1, the whole thing divided by 2. You multiply the whole thing out, so we got n squared divided by 2 plus minus n divided by 2, and then we have minus 1/2 here, right? No, yes. No, I got it wrong. Yeah, doesn't. Scratch that. Okay. Okay, so now the question is, which term, grows faster? N squared. Yep. So the order of magnitude is controlled by n squared. Even though, it doesn't grow quite as fast as actually n squared, pretty darn close when n is large. Is that okay? So that's the number of edges. So given that we have n vertices, the total number of possible edges is proportional to the square of vertices. Is that okay? But now, getting back to the algorithm, what is the complexity of the algorithm itself? If I tell you, oh, okay, we know the cardinality of E, how does that impact the algorithm? So let's switch back to the algorithm first, okay? And, huh? Oh, we have a loop inside a loop, and we have a conditional statement inside a loop, inside another loop. So it's a triple loop kind of thing. But there's a one conceptual constraint here that can tell you it's like, oh, okay, so that has to be the upper bound. It cannot exceed that. So what do you think it is? Okay, from our example, we have already shown that we can revisit the same vertex again. Okay, we can take a vertex out of Q and then put it back in. Okay, so that means, oh, okay, so maybe that doesn't give us a clue. Okay, have we ever reconsidered the same edge more than once? No. Of the entire trace, have we reconsidered the same edge more than once? Nope, we have not. So So it cannot. So the cardinal. So the number, the amount of time it takes to run this algorithm, cannot exceed something that is proportional to the number of edges. So it will be bound between those two, the number of vertices and the number of edges. If the number of vertices is really huge, yes, that, and they're all destinations, that would determine the amount of time it takes, because we have to basically remove one vertex at a time, and we have to go through the loop that many times. Okay, so that's the really long answer to that question. So now comes the short part of that question, is you just look up Dijkstra's algorithm.
So Google it.
You go to Wikipedia, and then you go to complexity. So the complexity is E plus something, something, something.
Oh, that's how the thing looks spread out. Okay, I never knew that. Don't judge me.
I was actually wrong, because they have to add the amount of time to sort the vertices too. So that's why there's the V log V here. That's the amount of time to maintain the heap. Because when you add something back into the heap, it takes time for that item to find its rightful place. So that is the other factor. But that's the worst case scenario. And this is the average case scenario. So it's not too bad. In other words, we're not seeing any squared or any factorial like that. It is not a slow algorithm by any means. Are we doing okay so far with this?
Usually you don't have a lot of destinations, like.
Yes, that is correct. You typically do not have a lot of destinations. So we only got 5 minutes left, so I just want to give you a context of Dijkstra's algorithm and how it is applied in, well, I wouldn't say real world, but it's robotics. Okay, so we want to look at micromouse. Some of you have seen this already, because this is one thing that I kind of show up. Oh, yep. So in a micromouse competition, you have a maze that is on a wooden board. There are 16 by 16 cells. The center 4 cells are designated as your destination. So if your robot reaches one of the 4 cells at the center, it is considered, at the destination. The maze configuration of the maze is not known ahead of time. So your robot goes in with no assumptions whatsoever of where, of the configuration of the partitions. So the job of the robot is really try to figure out the shortest way to go to the destination. So one quote-unquote run is one run from a corner to the center of the maze. That's called a single run. So they would basically time all the runs that you can do in 10 minutes. And then the shortest run, or the run that took the shortest amount of time, would be used to compete against other teams. So that's the whole thing about the micromouse competition. Do you see how Dijkstra's algorithm comes in handy? Every single cell can be considered a vertex, and then depending on the partitions, you're basically saying, okay, if there are no partitions whatsoever and your robot can only go north, east, southwest, then naturally each vertex has 4 neighbors. Is that okay? Making sense? But since you can put walls or partitions between the cells, then you're eliminating those particular edges. So your graph is basically just representing the actual configuration of the maze. Now the interesting part of micromouse is initially there's nothing on the maze. In other words, initially your graph is fully connected. Well, I wouldn't say fully connected, but every single cell connects to all 4 neighboring cells. Is that okay? But as you explore, your sensors will tell you, oh, there's a wall in front of us, okay? Or there are walls, to one side or to the other side. So you start to update your graph. Your graph actually changes over time. So every time you change your graph, you rerun Dijkstra's algorithm, so they can say, from where I am at this point, I should make a right turn now to get to the destination as quickly as possible. So this is really interesting, because it is doing this with every cell it explores, it is one, updating the map, which updates the graph, and then it reruns Dijkstra's algorithm to find out at that point what is the shortest path to a destination. So it explores and it tries to go from the current location to the destination as quickly as possible, even while it is exploring. Yep.
So this is kind of something I've been having trouble understanding. So it runs Dijkstra's algorithm, right?
Yep.
But like if we go back to the E prime we had in the example earlier, there's B A A E D A. But then let's say it is currently sitting in B. So it runs Dijkstra's algorithm.
Yeah.
But then has to forget everything else.
No, it doesn't forget anything. It's okay. Dijkstra's algorithm, in this case, it's represented in a different way, but conceptually, it is Dijkstra's algorithm. So what you do is you look up the E prime, and you go like, okay, which edge is starting with my current location?
Yeah.
You grab that edge and go like, okay, where should I go? To the left. Okay.
Okay.
So the interesting part about this is the efficiency of the algorithm. So given this particular application, okay, we have 16 by 16 cells. Things can be connected to up to 4 neighbors. Okay, so the connectivity is not really too bad. Okay, because every cell can only hook up to 4 neighbors. How much time do you think it would take to update and run one single run of Dijkstra's algorithm? On okay, so because I cannot say about time unless you know the architecture. So we are talking about an architecture like a 16 megahertz 8-bit processor called the AVR, which is used in the Arduino controllers. So the question now, 16 megahertz, it has got usually about 64 kilobytes of program space and 2 to 4 kilobytes of RAM, which would include your stack, your global variables, and so on. So the question is, how long would it take to finish Dijkstra's algorithm on a platform like that? Just guess. Order of magnitude question.
0.005 seconds.
No, not quite that fast.
More like 8 minutes or so.
Not quite that slow.
That's slow, man.
Not quite that slow. It just has to keep up with the exploration, right? Because as you're going, you go like, oh, there's a new wall here. Update the map, run the Dijkstra's algorithm again. So
2.5 seconds.
you got the digits right, but the decimal point is wrong.
5.2.
0.2 seconds. You're off by just 1 order of magnitude. 0.02. 0.025 seconds. It only took.
Well, how fast is the mouse though?
The mouse is not that fast. I mean, the ones that we do is not that fast. Now, there's an international class. Okay, so we are running out of time, but it is kind of fun to watch this. So. Okay, skip. Can I skip? Nope. So this micro mouse here is in exploration mode because you can see it's not really going crazy fast. This is the mapping run. Oh yeah, the Japanese robots are crazy fast.
Well, China's catching up.
See how it's going faster now? The mapped portion, it will go faster because it already knows where the partitions are. And this is what it does when it's using the Dijkstra's. Okay, now it's found it. Okay, now you can, that's the first run. It's still exploring right now. It's still exploring alternatives. Okay, so let's. Okay, I think this might be one of the speed runs already. So check this out.
Whoa. Hey, that's not fair. Let's go diagonal.
Yep, we can go diagonal. These ones can.
5.2.
Yeah.
5 seconds.
Okay, I'm running out of time. Now go on your own time. Go look for Micro Mouse and UC Davis. UC Davis represents of the region, the IEEE Region 6 is where Davis is. So when I was teaching this class, we were the top dog of all the micro mouse competitions, student, competitions. But when you look at the actual runtime of our mouse, by comparison, it's like limping along. It's like this. And it's wobbly. This is like solid, man. I mean, this thing just go like that. Yep. Yep. So check it out. There are no micro mouse projects anymore at UC Davis. Since they let me go because of the budget crisis like many years ago. They never really reinstated that class. So.
The budget crisis is over. How much they're charging?
Well, okay. I'm gonna turn off the mic first.